Everybody to the CMR Journal Club today. Today from broadcasted from Montreal, but with international and especially European attendance. So as usual, please unmute yourself or mute yourself if you're not speaking. Today we have two very interesting papers. And we're very fortunate to have the first authors here, and especially having Steffen Petersen. He leads the cardiac imaging part for the UK Biobank, and is of course most well known to everybody here. And we also then have Jannike, and she will present her paper thereafter. But without further ado, we only have 30 minutes. So we'll jump right into the first paper published in the European Heart Journal of Cardiovascular Imaging. And it's called European Association of Cardiovascular Imaging Expert Consensus Paper, a comprehensive review of cardiovascular magnetic resonance normal values of cardiac chamber size and aortic root in adults, and recommendations for grading severity. So a very important paper in times where we need a lot of standardization among all the different centers. So Steffen, thank you so much for joining, and take it from here.
Thank you, Matthias. So thanks for asking us to present this, because I think that's a nice reward for the work that we've done, that people think it's a clinically important manuscript and consensus paper. So thank you for that. Before I start, I'd like to really thank all the authors that you see here. Mohammed, Khanji, who's done a huge amount of work and is a very deserved joint first author. Sven Plein, Patrizio Lancellotti, and also Chiara, who've done a huge amount of work with me on this paper. It's been a very long project, actually, to get it through, and that was also because it underwent a very, very rigorous review process as part of the ESCVI scientific documents committee. We made a mistake, actually. So I want to just say that at the beginning, the paper was published without actually acknowledging the input of the reviewers. Now there's been an erratum at the very end of the paper. You can see the names of all the people who've reviewed the paper and actually really spent it. This was about 5 or so review rounds where we had to basically address the reviewers' comments. And you'll see it's about 10, 15 people, and they really all did a lot of work to make the paper better and to help shape it. So it really is a consensus paper, even though it only has 5 authors. The reviewers really have done a significant amount of work, and I'd like to acknowledge that. So let's start why we did this. Basically, the idea is that patient outcomes are can be influenced by cardiac MR, but that this is very difficult to prove because you have a lot of steps that can go wrong from acquisition or referring a patient to basically improving patients' quality of life and life expectancy. And there's a lot of papers that this paper hopefully will complement that talk about standardization, because you can improve the quality of cardiac MR and therefore increase the likelihood of improving patient outcomes by standardizing cardiac image acquisition, cardiac image analysis, and cardiac image reporting. There are separate papers on this published by CMR that I think are really important and complement our work here. Also, to improve the quality and the standards in the ESCVI, but also CMR has a certification process for individuals to basically document that people have can do cardiac MR. Let me just see how I'll go to the next page. So this paper fits in somewhere there to basically hopefully improve communication to referring physicians, to make it easier for referring physicians to understand what these numbers mean that we are reporting on ejection fraction, on end diastolic volume, because they're not all familiar with that. And whilst we do have the advantage with cardiac MR to measure continuous variables, which clearly has more information than collapsed information, that, for example, grading the left ventricular volumes into a mildly or moderately or severely dilated left ventricle, we felt that it is important to be able to communicate more clearly in categories because if the message doesn't get across that you've got a severely dilated left ventricle by providing continuous data, then maybe patients don't get treated optimally, which then may lead to suboptimal outcomes. So that is basically the premise of this paper, to say, well, when we have normal reference ranges for all of these measures we can do, how can we basically better communicate the degree of abnormality if it is abnormal? And usually we wanted to classify it into mild, moderate, and severe abnormality if it was abnormal or normal. So what we did is we did a review of the literature for normal reference papers for a number of the parameters that we report clinically quite often. And then we basically had a number of different approaches to classifying the severity, the severity. One approach was basically based on standard deviations. As most of you know, this is what a lot of the normal reference papers do. You've got an average and you've got plus minus 2 standard deviations, and that basically is pretty much your normal reference range. And then if you can say between 2 and 3 standard deviations away from the average, then it's mildly different. If it's 3 to 4 standard deviations, it's moderately different, and more than 4 standard deviations, then it's severely different from the normal. The second approach was to use percentiles rather than the standard deviations, which has benefits sometimes for not normally distributed data. And the third approach was basically to use consensus approach, which, for example, we used for the ejection fraction grading, because sometimes when you use the statistical approach, your reference ranges don't make good sense. Maybe a bit too tedious to go into the detail why that is, but then basically we sort of looked at how, for example, echo grade ejection fraction into mild, moderate, and severe. And we came up with a consensus based on our experience comparing cardiac MR and echo data, how we would best grade it. Yeah, so that was basically about the method. Let me just see whether there's anything else I wanted to highlight here. So what we didn't do in this paper is basically come up with recommendations how you should analyze your cardiac MR images. So that's been reported elsewhere as a consensus paper. We also did not do a meta-analysis as such, or we did not create our own reference ranges. We basically just used what was in the literature. And I think that is a key point to make sure when you want to use the tables that we produce in terms of the grading recommendations, that if you're using a particular grading recommendation, then you need to make sure that you are analyzing the images in a very similar way to what the normal reference paper published and how they analyzed it. Because as we all know, it makes a difference whether you're including papillary muscles into the LV volumes or into the LV mass, for example, or if you measure annulus measurements of the aorta in systole or diastole. So you need to make sure that if you're using any of our tables, which is based on a normal reference paper or a number of normal reference papers, that you're using the way they have analyzed and described the way they analyzed the cardiac MR scans. But what we also felt this paper would provide is a framework of how, if in the future new reference ranges come out in a larger cohort or in a maybe in a different ethnicity that is more applicable to your patient population, then you can use this approach that we've provided here to basically create your own grading system for your own reference range. So this is more in principle how we think about grading papers, grading our phenotypes. Now, let me just go to some other pages. I'm not going to show you too long the tables. We can go through that in a minute, but maybe just show you this table that basically you do really need to look at how the volumes were analyzed, for example, papillary masses included or not. And then here are some advantages and disadvantages of the different approaches, but we're not proposing a particular one. What I did want to say is some of the limitations of our paper that we are aware of and we list, because I think that's, I'll just jump to that. Oops, one back. So I think this is the sort of, hold on, there's one more. The limitations basically are that, sorry, just need to orient myself on this. So the normal reference ranges for the right end diastolic volumes indexed to the body surface area using SSFP-Cine imaging, they contain cutoff values for major or minor criteria as part of the ARVC task force criteria, which, you know, was published by Marcus et al. A few years back. It's really important to remember that the ARVC task force criteria were developed largely based on gradient echo CMR, which is known to underestimate the volumes due to lower incomplete endocardial border definition. And arguably, the ARVC task force criteria may need updating based on contemporary SSFP-Cine normal reference ranges. So let me just show you what I mean, or what we mean by this. If we go to the table with right ventricular ranges, based on the Cavell-Böhm paper, if you're looking at the normal reference range of right ventricular volumes for women and for men, you can see that the reference ranges basically are inclusive of the cutoff values. So if you're looking at the end diastolic volume per body surface area, they already include the cutoff values and already would potentially fulfill or contribute to a minor criterion for the ARVC criteria. And we believe that this is mainly due to the different Cine sequences used. So it's just something to be aware of. The tables are basically ordered generally, as you can see, into sort of the normal reference range, mildly, moderately, and severely abnormal for men and women split. What we haven't done is basically provided by age decade normal reference ranges. And the reason for that is that basically you can create this yourself if you want to, based on, for example, the Macera data, but we felt that this would not make a huge amount of sense given the fairly small number of subjects in each decile per gender. So if you're looking at the Macera paper, there's 10 women in each decile and 10 men in each decile. And this doesn't really give you very tight reference ranges. So we felt that this needs to be done maybe in the future when, for example, from UK Biobank or from combining other normal reference papers, we've got larger numbers in each decile, age decile, so that we can provide and update these numbers. So bottom line is this is an attempt to help you communicate a little bit more clearly to referring physicians what a normal value is and what a mildly, moderately, severely abnormal result is. But we are very aware that these numbers will have to be updated in due course as more reference ranges become available in different ethnic groups, in larger numbers, in particularly that we can then also provide age-related normal reference values and these gradings associated with it. So I think that sort of describes what this paper is about. I don't think it's very interesting to you if we just stare at the tables, but I'm happy to basically, you know, if you've got any particular issues, we can look at that. But I think otherwise the tables hopefully are self-explanatory.
Well, thank you very much, Steffen, for walking us through the initiative. I think it's very important to standardize the methodology to grade, because we all know that sometimes for clinicians who are not necessarily have these tables that they don't really understand if we tell them there's the numbers. And then the other alternative that someone just based on their experience says, yeah, well, this looks to me like moderate. That is also not very helpful. So I think that was a very, very important initiative. And as you said, we will probably have a flurry of new papers on reference values given the access to data like the UK Biobank and other bigger cohorts. So ideally, of course, one would think, have you thought about providing this your approaches to something like let's say a software solution or an app where people can update that using other reference values, or that you work with other people who are putting together reference values? I know, for example, John Afilalo here at Montreal, here in Montreal at the Jewish General, he's currently writing a huge consensus paper, meta-analysis, and that would of course be great to use this methodology.
Yeah, good point. So we have been thinking about how we might do that. So I guess a good way would be to create a website, normal reference ranges, cardiac and normal reference ranges, where people can basically send us their publications or send us their reference ranges with a description of what they've done, and you can put it out there and people can take it or leave it. That might be one way of doing it.
Okay.
The method is actually not that difficult. Obviously, it's just for most of the values, it's just a statistical approach. I wanted to do one more thing I've forgotten in terms of limitations that we are aware of, which obviously came back as a criticism from many of the reviewers, but also, obviously, I know that from my own practice, if you've got a patient, so the categorization isn't absolute. So I can overwrite, even if, let's say, I program these values into a reporting tool that automatically then classifies your end-diastolic volume maybe as moderately dilated, ventricle. I can still overwrite in the free text and say, this is actually a severely, or let's say ejection fraction is moderately reduced. I can still overwrite and say, actually, in the context of concentric hypertrophy and in the context of severe mitral regurgitation, this is actually really poor LV function. So we are aware that these categorizations obviously have to be considered in the context, clinical context, that if you've got concentric hypertrophy, your ejection fraction would actually be expected to be higher to be normal. And the normal ejection fraction might already not be normal anymore. And similarly for mitral regurgitation. So this is a known limitation, and we've acknowledged that in the paper. That's just something to be aware of.
Okay, thank you very much. Steffen, if I could ask you to unshare your screen. And I welcome Jannike Nykander from the Karolinska Institute in Stockholm in Sweden to present their paper that was done also with Martin Ugander as the senior author. And it's on tissue characterization, and specifically the relationship of tissue characteristics as defined by CMR to physiology. And I find this always very important, because I truly believe if we understand physiology, we understand the disease. And if we can see physiology or pathophysiology, we understand the patient. So this paper is called The Relative Contributions of Myocardial Perfusion, Blood Volume, and Extracellular Volume to Native T1 and Native T2 at rest and during adenosine stress in normal physiology. And Jannike, thank you very much for joining, and we're looking to take it from here.
So, thank you so much. Does everyone hear me, or at least Matthias, do you hear me?
Yeah, I think everybody can hear you well. Thank you.
Oh, great. So thank you so much for having me to talk a little bit about this paper. You've already presented the title, and I just think I'm just going to go through the figures and tables. The idea for this study originated with the fantastic publications that have been coming out from the Oxford group, who have been looking at stress native T1 mapping to identify obstructive CAD and also a microvascular dysfunction without gadolinium contrast. And there have been a few publications over the years, with I think the most prominent one being the one in JACC last year, where they could really show how well adenosine stress with native T1 mapping performed with regards to identifying patients with both obstructive CAD and microvascular disease. Then we wanted to understand what are the physiological basis for using native T1 mapping to identify obstructive CAD or microvascular dysfunction, and if this too would apply to native T1 mapping. So we set out to do this, and to do it, we included healthy subjects. So we had 41 healthy subjects with 51% females that underwent cardiovascular magnetic resonance at a 1.5 Tesla system. And I'm going to start here, which is figure 1, where we look at the timeline of the CMR scanning protocol. And as you see, we started out doing scouts and CINEs, and then we did native T1 at rest and native T2 at rest. And then we started our adenosine stress infusion at 140 micrograms per kilo per minute. And after 3 minutes, we did native T1 stress imaging and then native T2 stress imaging. And then we gave contrast dose of 0.05 micromolar per gram of gadobuterol, which is Gadovist, and we acquired this quantitative stress perfusion map and blood volume map that was recently published by Peter Kellman and also validated by Henrik Engeblom in Lund against PEP perfusion. And then we stopped our adenosine infusion and we waited for 10 minutes, and then we gave a small dose of Gadovist again to get perfusion maps at rest and blood volume maps at rest. And then we added to double up to do a double dose of contrast. And then we waited 10 minutes for contrast equilibrium. And then we did T1 mapping for double dose at rest to render ECV at rest. And then we started adenosine stress infusion again. And after 3 minutes, we did T1 mapping for rendering stress ECV. So this is a really important image to stress the fact that we actually have rest ECV, where we did T1 mapping post-contrast and native T1 mapping at rest, but also native T1 mapping at rest and T1 post-contrast at stress to really get rest ECV and stress ECV. One of the issues that we had then when we were going to analyze was that our apical stress ECV maps were not of sufficient quality due to partial volume effects, and also a sizable portion of the basal stress ECV maps were affected by through plane motion. So we only in the study analyzed midventricular images. So we analyzed both native T1, native T2, perfusion, myocardial blood volume, and ECV maps, both at rest and stress. And this is just the baseline characteristics of our studies. As you can see, we're 51% females, predominantly young, 26 years, and well, kind of normal volumetric measurements. And you can also see that they had quite a great response with the rate pressure product, and also both rest heart rate and stress heart rate that went up following adenosine infusion. And what we can see then here in figure 2, where we on the vertical axis have myocardial blood volume in percent, and on the horizontal axis divide by rest and stress, where you can see that myocardial blood volume increases during adenosine stress. And then in the middle here, we see on the vertical axis myocardial perfusion, and we have once again rest and stress, and you can see an increase in myocardial perfusion. And here to the right, we have ECV measured in percent on the vertical axis. And as you can see, there is a little bit more heterogeneity here, but still overall, there's an increase from ECV from rest to stress. And then looking at our physics, this is the physiology more, and then we have our physics parameters below, where we have on the vertical axis native T1 and once again rest and stress, and as you can see native T1 goes up, and to the far right here we have native T2 on the vertical axis, and as you can see it increases from rest to stress. And then what we wanted to do was to try to understand which or how the physics, the native T1 correlated with the our physiological parameters, myocardial blood volume, myocardial perfusion, ECV. And given the fact that we had a normal cohort or healthy volunteers with a very low measurement variability, we what we did was that we looked at, native T1 and myocardial blood volume as a continuum of physiology. So we entered this both rest and stress and made it to one parameter in order to really understand what is happening throughout this physiological states. So we can see here on the vertical axis, we have native T1 and myocardial blood volume, that there's a correlation of R squared with 0.43. And then we have myocardial perfusion with native T1, and the R square is 0.53. And then we have ECV and native T1, and the R square is 0.57. And looking at native T1 against myocardial blood volume, we see an R square of 0.59. And native T2 with myocardial perfusion, an R square of 0.61. And then we have native T1 and ECV with an R square of 0.35. So we can see that there are correlation between the physics and the physiology in this case. And then we wanted to understand which physiological parameter that correlated with native T1, or it can explain the changes that we can detect during adenosine perfusion. And then multivariate linear regression showed that it was myocardial perfusion and extracellular volume, both for native T1 and native T2, that had the greatest, that could explain the changes that we observed during adenosine stress. And then we pose this figure here where we just try to understand what is actually happening or when we have the rest and stress states. And what we can see, we have here in the rest state, looking at 100%, the relative contributions of 100% of LV mass, where we have the myocardial blood volume, which is 9% at rest, with plasma and red blood cells. And then we have our ECV, which is plasma and interstitium at 27%. And during stress, this increase to myocardial blood volume of 12% with red blood cells and plasma. And then at the ECV increases to 31%, which is interstitium and plasma. And there are a few things that are unknown here. Is that, first of all, does LV mass increase during adenosine stress? We don't know. And furthermore, we don't know if myocardial blood volume, or sorry, if red blood cells and plasma increase in 1-to-1 due to the fact that most of the increase in myocardial blood volume in the heart during adenosine is happening in the capillaries, where the ratio between blood cells and plasma might not be the same. So with this, we conclude that myocardial native T1, T2 perfusion, myocardial blood volume, and extracellular volume all increase during adenosine stress in healthy subjects. And the changes that we detect in myocardial native T1 and T2 during adenosine stress can largely be explained by the combined changes in myocardial perfusion and ECV. And also then poses, this is the physiological foundation on which we can use native T1 mapping and T2 mapping to identify obstructive CAD or microvascular disease.
Thank you very much. That was fantastic. In short, you were able to discern the physiology behind the observations. And what I liked is a lot that MR really now has made it out of the silver screen era of black and white, because we're mostly showing our color coded maps, which is a nice thing. I have two questions, one fairly practical and one more for the future. And whoever wants to also ask a question, just feel free to type it into the chat dialogue or just unmute yourself. So the question I have is, your experience that the apical maps, especially for ECV, were not that great is probably something everybody can share here. And I certainly have my issues with any of the mapping of the apex. So in fact, for some techniques and for shortened protocols, we're using only two slices. One is between basal and mid, and one between mid and apical levels. And so we have two slices only and not three. So is it is it too harsh to say that the apical slices most often are pretty useless, even for the maps? Sometimes sometimes maybe not for the perfusion. What is your take on that?
Well, I would say that T1 maps at rest, during rest imaging, I would say T1 maps, T2 maps, no problem doing imaging of the apex. Sometimes you run into trouble with the ECV in the apex, but mostly I would say that is due to that the pre and post contrast T1 maps have been acquired at different breath holding states. So it's a lot of cooperating with your patient or your healthy subject in order to get the correct breath hold. But for stress ECV, you both have a higher heart rate, and also with the adenosine in the blood, the patients or the subjects, they tend to have higher respiratory rates as well. So we did not experience, any success, I would say, with imaging the apex during stress. So overall, at rest, usually no problem, but at stress for ECV, a problem.
Yeah, and then, although we are already a little bit over the time, one question, of course, the obvious one, if there is such a good correlation with T1, especially T2 for perfusion, although the overall contrast to noise is not that great, but is it time to, or maybe you're doing that already, for studies using just native T2 mapping with a vasodilator such as adenosine replacing contrast-enhanced perfusion?
Well, we don't have as extensive experience as I guess the Oxford group has, looking at their publications with doing native T1 mapping. Yeah, with native T1 mapping for obstructive CAD. We have 2 studies ongoing, and the right answer, or the answer right now, is that no, we do our clinical stress perfusions with contrast, and we are looking to gain more knowledge on how to use native T1 and T2 for diagnosis of CAD or obstructive CAD and microvascular dysfunction.
Okay, thank you. So can I ask you then, Jannike, to unshare your screen?
Yes.
Any other questions from the audience? If not, then I just wanted to briefly point to the next journal club. We will have a break now over the holiday season, and the next one will be in January, on January 14, and we will have a focus on myocarditis, because there's a lot happening these days. So especially after the update of the Lake Lewis criteria, and this is one paper here coming from German center in Kiel and Hamburg, and they're looking at strain imaging for myocarditis. So what is the added value of strain imaging? And then we have a paper, the first author, Bettina Bessler. She already performed some interest and published some interesting studies on an advanced analysis of tissue characteristics in myocarditis. And there's a paper, also multi-center paper with Philip Lourdes as a senior author. And it's about T1 and T2 maps in myocarditis in acute versus chronic symptoms of heart failure. And then we will also show, as a third one, just briefly, a letter from the ITAMI registry in Italy on the impact of pericardial